Our second speaker of this morning is Dr. Shai Feldfogel from Technion-Israel Institute of Technology. We're very pleased to have him coming all the way from Israel to come and give us a presentation on 2-degree debonding evolution in FRP strengthened plates under combined loading. Thank you so much.
Hello, everybody. Good morning. I'll be talking about two-dimensional effects in debonding in FRP strengthened plates. The loss of structural integrity in multi-layered structure in general is inextricably linked with interfacial debonding mechanisms, as we have seen in the previous lecture. In FRP strengthened structures, we know the edge debonding mechanism, which we can see here. We know of the crack-induced debonding, typical, and the lamination-induced debonding, where by the lamination I mean initial locations of interfacial separation. By debonding, I'm referring to the process of the beam becoming interfacially debonded. Okay. If we consider debonding in beams, two main characteristics of the process are one-dimensional kinematics and two-dimensional interfacial tractions. By one-dimensional kinematics is meant that the debonding geometry, the geometry of the process can basically be reduced to the tracing of a single point along a known line. By two-dimensional interfacial tractions, I mean that we have basically a tangential shear component, Tx, and a peeling traction, Tz, at the interface between, let's say, the concrete and the adhesive. It can also be between the adhesive and the FRP. This is just to represent this. If we consider the problem in plates, it is more complex. Consider in a gray a concrete plate strengthened with an FRP patch. Okay? In this case, we'll see that the kinematics are two-dimensional as opposed to one-dimensional, and the interfacial tractions are three-dimensional. The debonding mechanism, which is denoted here by this, the debonding front is denoted by the red line, could, for example, develop in such a way, qualitatively. Okay? And we see that the area and the shape and the location of the debonded region changes, as opposed to the 1D beam case where it's just a point along a line. Here it's change of area, location, size, etc. In addition, on top of the two traction components we have in beams, we have added component, width component in plates, and along with it goes another interfacial traction component, which makes for a full 3D traction state at the interfaces. The essential questions regarding interfacial debonding in plates are: what is the threshold load under which the debonding mechanism will initiate? How does the debonded region changes in size, shape, location as the mechanism develops? How are the interfacial tractions distributed along these contour lines? Is the process stable or not? We've seen in the previous lecture that the force deflection curves suggested instability of the mechanism. As well, we have the laminations, which are frequently encountered in laminated layers, and they also play a role in the development of interfacial debonding mechanisms. And lastly, the effect of all these parameters on the structural resilience. The modeling challenges involved in modeling this process is first to simulate the process of interfacial separation, and second, to capture the three-dimensional traction state at the interfaces and at the soft adhesive layer along the contour of the laminated region, the bonded region. To deal with these challenges, a methodology is needed that can be localizable. By that I mean that it can focus on the high gradients that occur along the debonded contour. It should also be geometrically flexible in order to capture the geometric irregularity of the debonded region. And lastly, it should be able to capture the snapback type behavior that is typical of the debonding mechanism. 3D, you don't see it, but it's 3D finite element analysis is a natural choice to deal with these modeling challenges. However, a very fine mesh is required to capture the high gradients in the adhesive layer. It's meshing across the thickness. This meshing across the thickness is inevitably percolates to the concrete layer and also to the FRP layer, inevitably. This, when you consider a plate, is extended towards the lineal dimensions of the element and results in a very high computational burden and expensive computation. A computationally more efficient alternative to the 3D approach are two-dimensional finite element plate models, where no thickness meshing is required, thus making the computation much more economic and quick. In the paper by us, Feldfogel and Rabinovitch from this year, we modeled a strengthened plate or narrow plate or beam using the 3D approach and the two-dimensional approach, and there is a factor of about 130 degrees of freedom less in the two-dimensional approach, which speaks for itself. Okay, the two-dimensional approach or the stacked plate approach means that we take plate models, one element per layer, and we represent the interfacial relations between them with interface models, which are, in essence, describe the interfacial tractions as function of the interfacial separation. This is a typical bilinear representation of this relation, which accounts for the bonding mechanism. The layers are typically taken as Kirchhoff plates or Mindlin plates without shear deformation or first-order shear deformation, and sometimes they're taken as degenerated solid elements. The interfaces may be represented as bilinear or exponential in particular cases. The Borscht and Remmers used this approach using a solid plate model in order to simulate two-dimensional debonding in a glare panel subject to compression, to in-plane compression. It is partly delaminated in this circular region and compressed, and they used this method successfully to simulate the failure mechanism. This approach is satisfactory when the layers are quite similar in elastic moduli. However, in some cases, such as soft-core sandwich panels and FRP strengthened plates, we have a soft layer. In the case of FRP strengthened plate, it is the adhesive layer, which is much more flexible than the neighboring substrate or concrete layer and the FRP layer. The standard plate models used in the stacked plate approach are incompatible with the high deformability of the soft layer, which gives rise to localized stress concentrations and high gradients. In order to deal with the deformability of the soft layer, the high-order approach has been used. The high-order approach assumes an enriched displacement field across the thickness of the soft layer and results in an important consequence of this assumption is that the transverse normal stresses, sigma zz, which are generally neglected, are here not neglected and vary linearly across the thickness of the soft layer, which is necessary in order to capture the three-dimensional stress state and traction state at the adhesive and neighboring interfaces. In plates, this method has also been used. Here we have an added dimension, of course, the y dimension, and these are the displacement fields in the soft adhesive layer. We see that on top of the displacement terms that designate the standard plate theories. This, for example, represents a plate theory with first-order shear deformations. These are the terms of the enriched displacement field, which corresponds to the high-order modeling, and which gives rise, for example, to this linear variation of the sigma ZZ in the soft layer. This method has been used in the same paper cited before to model a concrete plate strengthened with a central FRP patched, and the FRP patched was assumed to have an elliptical inclined delaminated region initial. And the plate was subjected to a uniform loading, thermal loading. In this model, the interfaces were assumed infinitely strong and linear. Okay? And using the high order approach, the sigma ZZ along the contours of the delaminated regions, where in this case the mechanism would begin, can be quantified. Okay? This thing shows the out-of-plane deflection contour map, which is, we see here that at this region, at some point, this delaminated region buckles. Okay? And so we see high gradients and large deformation in this region. Okay, so to summarize the literature survey, we see that we have existing stacked plate approaches which do not account for the full deformability of the soft layer. On the other hand, we have existing high order approaches which use infinitely strong interfaces and thus cannot account for the development of the bonding mechanisms. This constitutes a gap of knowledge, and the essential questions raised before with respect to the behavior of the bonding, interfacial debonding in plates, remains unanswered. The purpose of the present work is to bridge that knowledge gap by combining the high-order modeling with three-dimensional cohesive interface modeling, which will enable to account for the process in FRP strengthened plates and gain insight into the triggering of the debonding mechanism, its evolution, its stability characterization, the effect of the laminations, etc. Okay, so the formulation is based on three layers: the typical substrate layer, an adhesive layer, and an FRP layer, each one having its own coordinates. Okay. Now, the displacement field assumed for the three layers, for the two rigid layers, the concrete and the FRP, a standard first-order shear deformation is assumed. And the special thing is that for the adhesive layer, the enhanced displacement field of the high-order modeling is used. Okay, these are the strain displacement relations, and nonlinear terms are taken in order to account for buckling of the laminated regions and nonlinear behavior in general, not geometrically nonlinear behavior. Okay, this is the same for the soft adhesive layer. The only difference is that in the adhesive layer we have the transverse normal deformability, which is not existent in the substrate and FRP layers. These are orthotropic constitutive relations for the two rigid layers and for the adhesive layer. Okay, if we want to talk about the interface modeling, we start with classical two-dimensional interface models, which are known from beam models. Okay, essentially, as I mentioned before, what they do is define the interfacial tractions. In the case of beams, it is the peeling traction and the tangential traction Tx as function of the corresponding displacement jumps across the interfaces. Typically, they look like this for the peeling traction, Tz, representing the debonding, and for the tangential traction, they look something like this. The advantage of these things, these theories, as we have a large body of, in the literature, of working with them and calibrating them, etc. Now, in plates, the problems that we face, we have an added dimension, as mentioned, And the two-dimensional B models cannot be directly used for these problems, since we have another traction component. So, to move from two-dimensional interface modeling to three-dimensional interface modeling, we first define a principal interfacial direction. The principal interfacial direction is seen here in red, is determined as the resultant of the tangential slip in the x direction, delta u, and the tangential slip in the y direction, delta v. It is actually the direction of the maximal slip, in-plane slip, at the interface. After defining this principal interfacial direction, we assume that a 2D cohesive law, which we have many models for, applies in this direction, and of course in the direction transverse normal to the screen, which is the z direction, which stays the same. Now, this two-dimensional cohesive law can be bilinear or exponential. It can be any particular model. The next step is to use this two-dimensional model in the principal interfacial direction to compute the tangential traction in that direction and also the peeling traction in the normal direction. And lastly, in order to obtain Tx and Ty, the Cartesian components of the tangential tractions, we simply project the resultant tangential traction in the principal direction onto the Cartesian axis. Thus, we obtain a three-dimensional cohesive interface. In this work, we used an exponential law, two-dimensional cohesive model, and using the steps that I outlined before, we obtain a full three-dimensional cohesive model. A principle of virtual work concludes the formulation of the model and is the basis for the two-dimensional multi-layered plate element used in this study. Okay. We used a linear triangular element which enables to deal with the geometric irregularity which is inherent in the problem at hand. Okay, the finite element equations are derived the standard way, and shear locking, which is a numerical element of these type of formulations, is resolved using a work by Belichko et al., 84, and is outlined in full in this paper. In order to cope with the snapback behavior, which typifies the Debonding mechanism, an arc length procedure was used. Okay, to validate the model, comparison has been made to experimental results from Butler et al. In this work, they investigated the compressive strength of laminated composite subject to compression and with the initial delaminations. Okay? So here you see it's not to scale, but basically this is the structure. The inner circle designates a delaminated region, and the strength was defined by buckling of this sublaminate and by the threshold load under which the bonding mechanism initiated. The results were monitored using digital image correlation. The validation parameters to compare the behavior of the actual work in our model are the buckling load of the sublaminate and the threshold load for the bonding initiations. Okay, this is the final mesh, the two-dimensional final mesh in our work, using zoom-ins on the contours of the delaminated regions, which show the efficiency of the triangular element and the local mesh refinement capacities of it. Okay, to determine the buckling load, we consider the sublaminate out-of-plane deflection. So we see in this figure, plotting this out-of-plane deflection versus the load, okay, the applied strain. We see that at the beginning it is linear, but at some point it tends to infinity, indicating that the sublaminate has buckled. Okay. These are our model results, which indicate that the computed buckling strain is near 1,550, and the experimentally measured result from the Butler et al. Paper is between this number, which is in good agreement. This is a contour map of the out-of-plane deflections showing the locality of the phenomenon. The post-buckling behavior was examined by comparing the out-of-plane deflection contours of the model versus the experimentally measured one. So at about twice the buckling load, we see that these are the experimental out-of-plane contour maps, and these are the ones computed with our model. At about 4 times the buckling strain, you see that the contours has changed a little bit, become more elongated, differently oriented, and we see that our model captures this change, which validates the capacity of the model to capture the nonlinear behavior. 2 minutes? Okay, so I will jump a little bit ahead to get into the two-dimensional debonding effects in FRP plates. Okay, the purpose is to study the two-dimensional debonding effects using our model, stability characteristics, and the effect of the initial delaminations. So we considered a 4-point bending beam, okay? And we modeled it as a plate. This is a plan of the strengthened plate. This is a cross-section which is not clearly seen, but I think you can understand it from the view and the plan. Using double symmetry conditions, we only modeled the lower left quadrant. Okay. And we examined 6 cases, an undelaminated case and cases B to F, which have different initial delaminations. This is the finite element mesh, and this is a zoom in on the edge of the laminate where the debonding mechanism initiates. So, depending on the case, we can designate on the element level the properties of delaminated regions and non-delaminated regions. The zone of interest is which is refined, is where the mechanism initiates, okay? And which allows looking into two-dimensional effects. Okay, so if we consider case A without delamination, the behavior is shown in this low deflection curve, okay, which is quite linear until, and this thing is the stretched view of this point where the snap occurs. The snap defined by a snap load, R snap and delta snap. After which the load suddenly diminishes, which indicates an unstable behavior and the triggering of the debonding mechanism. So to understand the effect of the delaminations on this phenomena, in this table we compare the snap loads for each of the cases examined. So we see that the highest load, or the most resilient one, is the one without delaminations, naturally. And the one, case E, which have two delaminations right on the edge, is the lowest one, although the difference is not significant. This behavior, the bilinear behavior, is typical of all the cases which have delaminations on the edge, which are all except D and F, which have down the road delamination. Not on the edge, but down the road as the delamination continues. The next slide shows their behavior. We see here the stretched view, and the low deflection curve is quite strange. It's zigzaggy with increasing segments, OA, BC, and decreasing segments, AB and CD, which obviously are related to the down the road delamination. So to examine this, we take snapshots of the debonding front contour at various stages of the loading in the cases with the down the road delamination. So we see that point A, where the snap occurs, is when the debonding front has just passed the first delamination and has become straight. Okay? Now, point B, which is this, corresponds to the local stabilization of the mechanism, where the load again increases, representing a structural behavior, stable one. So the stability is associated with the debonding front becoming not straight and passing through traction. So here I wrote that debonding slowers are the compressive traction which the debonding front has to cross, and the front becoming not straight or two-dimensional by nature, irregular. Consider that there is a symmetry line, so this continues. You can imagine it. Point C, which is the second snap, again corresponds to the debonding front having passed through a delamination and becoming straight again. And the analysis terminates at point D, where the debonding front has reached the end of the refined mesh region. Okay, so to summarize, we have seen two-dimensional debonding effects involving the irregularity of the debonding front contour, even in a seemingly one-dimensional context of a narrow plate. We also see the arresting effect of the laminations on the mechanism and the two-dimensional behavior stability. To obtain this, we combine the high-order approach for the soft adhesive layer and three-dimensional interface modeling. And we saw that it is conducive to capturing these two-dimensional effects. The research was supported by the Israel Science Foundation, to which we are grateful. And thank you for the attention.